In the last few lectures, we have discussed the different important properties of central force field. You have seen that motion of a particle in a central force field always takes place in a plane. That is, this motion is always contained in a plane. You have also seen that a central force is a conservative force. And you know, whenever motion of a particle or a system takes place in a conservative force field, definitely the total energy of the particle or system remains conserved. Okay? Conservation of energy holds in a conservative field, you know. If the particle or the system is acted upon by the non-conservative force or dissipative force, energy does not remain conserved. But if the force acting on the particle is a conservative force, definitely its energy remains conserved. And as you have studied in the previous lecture that a central force is a conservative force, so it is obvious that whenever a particle will move in a central force field, its energy will remain conserved. So in this lecture, we will see the energy conservation in a central force field. How we can say that total energy of a particle remains constant whenever the particle moves in a central force field. We will prove it. And at the same time, you will also get a very useful expression for the total energy of the particle moving in a central force field. And that very expression for total energy will be invariably used in the theory which we will develop in the forthcoming lecture. So let us see how the conservation of energy can be proved for a particle moving in a central force field. For this, let us consider there is a particle of mass m and this particle is moving in a central force field. Let us see. See this figure. I have shown that this is an arbitrary path or a planar curve along which our particle of mass is moving, and during the motion at any instant the particle is at this point P. I have shown that the radius vector of the position of the particle with respect to the center of force, O is the center of force of the central force. Sorry, the page has been turned, but this will be just okay, so don't worry. This is just a minor defect of my device. So let us see here. It is now okay. You can see. I have considered that the particle is moving in a central force field, and at this point P, the particle is at any moment T. Now you consider a radial unit vector, this r hat, in radial direction as you have seen in the previous lecture. And the central force acting on the particle is F, as you can see in this figure. Now, in the definition of central force, we have seen that any central force is symbolically represented like this: F equal to F of r hat, where you know this F of r is actually the magnitude of the central force field vector F, and this F of r may be positive, it may be negative. In case of repulsive central force, this F of r is positive, and in case of attractive central force, it is negative. So this symbol for the central force, you can see from this symbol that the central force always acts on the radial line. This is just definition of central force. So if F is the central force acting on this particle, then this force will be either along OP, or it will be either along PO, you know, because central force always acts either away from this fixed point, which is called center of force, or towards the center, or towards this fixed point O. Okay, so a central force is completely on the radial line. So if you calculate the component of this central force in transverse direction. That is, this is transverse direction, and if you consider that this F theta is the component of the central force in transverse direction, obviously this will be 0, because central force is on this line, and from this line the transverse direction subtends an angle 90 degree, and the component of any vector in a direction at right angle to it is 0, you know. As I have told you that motion in a central force field always takes place in a plane. So if the particle is moving in a plane, in general, you can write the expression for F in terms of its components as F equal to Fr r hat plus F theta theta hat, where actually Fr is the radial component of this force F and F theta is its transverse component. But as you have seen that in case of central force, F is completely along R, okay, either in the positive direction of R hat or in the opposite direction of it. So instead of this F, in case of central force field, this equation has been written in general, but if you apply this equation for the case of central force, then this F is equal to Fr r hat, and that will be equal to this much, that is Fr r hat plus F theta theta hat. Now you can see that if two vectors are equal, the corresponding components are equal. So the radial component Fr of this force will be simply equal to Fr. And what will be F theta? F theta will be equal to 0, because in LHS there is no component corresponding to theta hat. So you can see that in case of central force, the force is completely on the radial line and its transverse component is 0. In simple way, you can say that the transverse component of central force is 0. So this force is completely equal to its radial component. Okay. So the magnitude of central force F is completely equal to F of R, that is radial component Fr. And according to Newton's second law of motion, you know this Fr will be what? This will be mass times acceleration in radial direction. Since this force is in radial direction, so what will be the equation of motion? That will be simply MAR. Okay. Now, in the previous lecture, I have discussed the expression for acceleration of a particle moving in a plane in radial coordinates, and we have seen that the expression for the radial acceleration AR is what? You can remember, I have told you in those lectures that these results must be always in your mind. So this is the expression for radial acceleration AR equal to R double dot minus R theta dot square, or in other words you can say that this is d2R by dt square minus R d theta dt square. This is the expression for radial acceleration. So now you can write the equation of motion. You have seen that F is equal to m times AR, and instead of this AR you can write R double dot minus R theta dot square. Okay, this is just a very simple calculation, you can see. And this can be written as mr double dot minus mr theta dot square. So this is the equation of motion of the particle moving in the central force field. Now you know I have discussed actually in the previous lecture the expression for the angular momentum of the particle. Okay, you have seen that the angular momentum of the particle remains conserved when it moves in a central force field, and dealing with this fact I have derived the expression for the magnitude of angular momentum, and we have seen in the earlier lecture that the magnitude of angular momentum J is equal to mr square theta dot. Can you remember? I have discussed this result. And so from this, if you find the value of theta dot, this will be what? This will be simply J over mr square. Actually, our aim is to express this expression for force acting on the particle in terms of the angular momentum J. So for this, you must replace this theta dot in equation 1 by this expression of theta dot, that is theta dot equal to J by mr square. So let us use this equation 2 in equation 1. And after using this, what you will get? You can see here that F is equal to, see the equation 1, mr double dot minus mr times theta dot square. But what is theta dot? Theta dot is J by mr square. So I have substituted here J by mr square instead of theta dot. Okay. Now after simplifying it, you can see that F will be simply equal to mr double dot minus J square over mr cube. So in terms of angular momentum J, this is the expression for the force acting on a particle of mass m moving in a central force field. Okay. Now as I have told you earlier, and you have seen this in the previous lectures, that a central force is a conservative force. And you know, any conservative force can be expressed as a negative gradient of the potential energy. So if you consider that the potential energy of our particle moving in this central force is equal to U, then you can write the force acting on this particle F is simply equal to minus du dr. This is a general fact. Any conservative force is always equal to negative gradient of the potential energy of the particle. The general relation we write in this way: F is equal to F vector F is equal to minus del U. This is the general result, minus del U. Minus del U means negative gradient of U. And in polar coordinate, where F only depends on R, you can write F equal to minus du by dr. Okay? But you have seen that the expression for F in terms of angular momentum is what? You have just seen that this is mr double dot minus J square over mr cube. So this will be equal to minus du dr. And from this, you can see mr double dot will be what? We will bring this term minus J square by mr cube in RHS, and this can be written as minus d dr U plus J square by 2 mr square. You can check whenever you will apply this operator minus d dr on this second term J square by 2 mr square, you will simply get plus J square by mr cube. Okay. So mr double dot is equal to this much. Now to find the expression for energy and its conservation, we have to apply a simple algebra. And remember this step. For this, you should multiply this equation for both sides by r dot. So multiplying equation 4 by r dot, we get what we will get after multiplying this equation 4 by r dot. You can see the LHS will be now written as mr double dot times r dot. Okay. And minus d dr U plus J square over 2mr square times r dot. Okay, times r dot. Now see, this product mr double dot times r dot, you can write this expression in this way. This can be written as d dt half mr dot square. You can check it. When you will differentiate this half mr dot square with respect to t, you will simply get this mr double dot times r dot. This is just a simple differentiation and you may check. Okay? And this is equal to minus d dr u plus j square over 2mr square and r dot. You know r dot means dr dt. R dot means dr dt. Now see the expression in RHS. Here there is minus d dr this much dr dt. So this RHS will be simply written as minus d dt and this much. So what will be our result? You can see this implies d dt 1 over 2 mr dot square, and this can be written as minus d dt j plus, sorry, not j, what is here you can see, this is u, not j. Sorry, this is u plus j square over 2m r square, 2m r square. Okay. Now you can see the operator in both sides of this equation is d dt. So this equation may be simply written like this. This can be written as d dt half mr dot square plus j square over 2mr square and plus u, and this equal to 0. This is 0. Now since the time derivative of this expression inside this square bracket is 0, so you know this expression in a square bracket will be definitely a constant, because derivative of constant is 0. So we can see that this half mr dot square plus j square over 2mr square plus u equal to constant. This will be equal to constant. You can take this result as an equation. Say this is equation 5. Actually you will see later on that this expression in LHS of this equation is nothing. This simply represents the total energy of the particle moving in this central force field. Actually this is just a sum of the kinetic and potential energy of the particle. Okay, but how you can test it? See here, we know, you have seen earlier that the expression for J is what? J is equal to mr square theta dot. You know, you have just used this relation. This is mr square theta dot. Okay. So let us substitute this value of j in this equation, and therefore what will be j square over 2mr square. You can see j square means mr square theta dot whole square and divided by 2mr square. Let us simplify it. You can see this will be m r square theta dot square and over 2, and this can be written as 1 over 2 m r theta dot square. Okay, but you have studied in the previous lecture that this r theta dot is nothing. This is simply the transverse component of velocity. So this can be written as half m v theta square, where what is this v theta? This is transverse component of velocity, and this is equal to r theta dot. Okay, and again you know that the first term in the above expression, which is half m r dot square, can you recognize? You have studied earlier that r dot means what? This is the radial component of velocity. So this is simply half m vr square. Vr is the radial component of velocity. So the above expression, that is in the equation number 5, now can be written in this manner. Instead of half m r dot square, you can write half m vr square, and instead of this second term, you can write half m v theta square. Okay, so write these two expressions here. So this will be half m vr square plus half m v theta square and plus u, and this equal to what? This is constant. Okay, now see, this expression can be written as half m vr square plus v theta square and plus u equal to constant. Okay, but you know that vr, which is radial component of velocity, v theta is transverse component of velocity. So vr square plus v theta square, this is simply equal to v square, where v is the resultant velocity. So this expression can be written as 1 over 2 mv square plus u equal to constant. Okay, u equal to constant. That is, you can say half mv square, this is simply the kinetic energy, u is the potential energy. So kinetic energy plus potential energy remains constant for a particle moving in a central force field. So in this way you can see that the principle of conservation of energy holds when a particle moves in a central force field. So energy remains conserved. Okay. Again from this, as I have told you, now you can see that the expression in LHS of this equation 5 is nothing. This is simply the expression for the total energy. The first two terms actually represents the kinetic energy of the particle, and u represents its potential energy. So I will again suggest you must remember this expression for total energy of the particle moving in a central force field, because this expression will be needed in the further discussion on this in this chapter. So total energy of a particle moving in a central force field. If you write it E, what will be the expression? This is simply half m r dot square plus j square over 2 mr square and plus u. U is the potential energy, and the value of u will depend on the nature of the central force, and so in a particular problem you will have a particular expression. So this is also a very important result, and you should remember whenever needed the expression for the total energy you should write this. Okay, I think you have understand that the total energy of a particle remains conserved in a central force field. In this way you can prove it. Now in the forthcoming lecture, first of all we will find the equation of trajectory of the particle moving in a central force field, and after that the very important theory based on this concept will be dealt.